A very warm good afternoon to one and all. I would like to greet and acknowledge our Honorable Chairman, Sir, Board of Management, respected Dean, Director, faculty members, and my dear friends. On behalf of Vivekananda School of Engineering and Technology and Vivekananda School of Information Technology, I would like to extend a very warm welcome to a remarkable inspiration, Dr. Brijesh Eshpuniyani, sir. He is a highly accomplished engineer, researcher, and an academician who has made significant contributions in the field of civil engineering, aeronautics, and biomedical engineering. Sir obtained his Bachelor of Technology degree in civil engineering from the prestigious Indian Institute of Technology, Bombay. After completing his undergraduate studies, he pursued his passion for research and further advanced his education by earning a Doctor of Philosophy in Aeronautics and Astronautics from Purdue University. Following the completion of his PhD, he continued his academic journey and held a postdoctoral research fellow position at the University of Michigan, where he focused on biomedical engineering. His areas of interest include fluid dynamics, transition and turbulence, high-speed aerodynamics, mathematics, including calculus, differential equations, and linear algebra. So, I invite you to please come up on the dais and lead today's talk.
I am standing in front of a bunch of students who are all computer science students, right? I don't have a single degree in computer science, right? But the case I want to make today is even after an education in computer science where you focus entirely almost on programming and the internet and artificial intelligence and a whole lot of new topics, there are avenues if you wish to go ahead and make contributions in more diverse areas, right? And even at the undergraduate level, it takes at the most 2 or 3 elective courses to get ready to do a project in what I am going to show today, right? So the leap of imagination is not much, but you just have to be ready for it. That's about it, right? You have physics in your first year here, right? You have mechanics, right? I'm going to make the bridge rather easily. Usually when I present this, I present it to people who are actively researching in the area. I will use about the same presentation, but I'll slow down. I'll slow down so that I can make these connections for you, right? And any time anybody has a question, ask, right? I like that. That way things get active. Okay, so the very first 3 words, a computational study, right? So the entire work that's being shown today is done on a computer. Right, and let me kind of inspire you a bit more. The Boeing 777 aircraft, all the way till the end, was entirely designed and developed on computers. Only the last stage they took it to a wind tunnel to test, and they flew it, and it works just fine. Right, so applications of computer science in very, very diverse areas are now commonplace in the industry, in academia, everywhere. Right, so I'm going to make that connection here. All right, this presentation is focused on supersonic missiles. Right? The DRDO has its own set of missiles. Internationally, there are a whole lot. So I'm going to spend, one slide on talking about what are the conventional ways to move a missile. You want to move it up, down, left, right, roll it. There are some conventional ways that have been used for the last 50, 60, 70 years. Right? They don't always work. They're not the most efficient at times. So there are unconventional controls, right? And I'm going to cover a couple of them. And then our proposed concept is a new kind of unconventional control. And we carried out a study to show why it might be a good idea to think along those lines, okay? And once I come to bullet point number 4, I'm going to have almost all of your attention, because then everything is being done on a computer with a computational domain. There are a bunch of governing equations which we have to solve. We apply a numerical method to solve them. We get the results, right? We know how to validate the code so that we can trust it, right? And then we analyze our results. And I'm going to show this. And again, there are parts where things go into too much detail, right? Too much of specific detail, and those slides I'm going to jump through, because otherwise I'll lose your attention. You'll say, what is all this? But the parts where I know that I'll stay connected with you, I'll spend more time, right? But I'm around after this, so if people want to ask more detailed questions, I'm well. All right. So I'll right in the end, then we show why we believe the proposed concept is actually all right. Not every proposed concept works. Ours, I think, works. And then I'll arrive at some conclusions. Okay. Now, the way this thing is placed, I'm going to keep looking like this. But those people shouldn't feel too left out, right? So if you have any questions, just say hello. I have a question or something like that. Okay. All right. All right. These are your conventional controls. There are essentially three kinds of ways to control missiles, right? The first kind is called the canard control, right? These are small wings right at the front of a missile. You must have seen a general missile during the Republic Day parade, and sometimes you see these very small wings right at the, they are called canards, right? And they work very, very well as long as the missile is almost horizontal, right? Suppose it's taking a steady flight from here to, who's our current enemy? Beijing. Okay, so here to Beijing, if it stays flat almost, they work well. But if you pitch up too much or pitch down too much, they don't work that well. The missile just kind of drops, the lift level drops. Okay, so there are advantages to it, disadvantages to it. All right, then wing control are these bigger wings in the center of the missile, right? These are better than canard for the most part. Right, that's why mostly they use wing control. Right, the advantage is that even with a little motion of these wings, you can actually move the missile around a fair bit. Okay, right, that leads to further advantages. Right, for example, if my missile is trying to lock onto a target and the target is moving, right, there is a smaller error compared to other controls because I can move fast, right, and I stay locked on even when I have to do a whole lot of things. I stay locked on the target. These are the advantages. Disadvantage, they need to be really large to do all this. Large wings means more weight. More weight means you need more propulsive power. There are disadvantages. Okay. Then these wings, if you have noticed, how do I explain? Even if a boat is going in a small lake, you will see that these circular eddies of water form behind it. They are called vortices. So these big wings actually shed these circular motions of air. When they come and hit the tail, they affect the rudder efficiency. So these are disadvantages. Again, there are advantages and disadvantages. Tail control is also a way where they use the tail to control. Okay. Now this is opposite to canard. Canard used to suffer at high angles of attack. Tail is excellent at high angles of attack. It works really well, right? But as I just told you, they are continuously affected by the wings, right? So there are some things you can do, some things you can't do, right? Now in order to start improving on these things, people came up with unconventional ways to control missiles, right? For example, there is a thrust coming out from the back which is creating the propulsion, right? So if I can find a way to just move this thrust vector, right, then Newton's third law comes into play, right? Every action has an equal and opposite reaction. So if I put the thrust upwards, my missile is going to start pitching down. If I can move the thrust downwards, I will go up, right? So people do that. You see those red arrows, right? They are all pointing in the up direction because that's what these pictures represent. You can do the symmetric thing. They'll point in the, so thrust vectoring, this is what, so that's an unconventional way. You're no longer using canards and wings, you're using the propulsion output to move the missile left, right, up, down, as ever you wish, right? Then there are reaction jets, right? Now these, from the missile surface, they shoot out a jet of air, right? What does this do? Okay, how many of you have heard of the sonic boom? This word, sonic boom, okay? Whenever anything flies faster than the speed of sound, right, what happens is a shock wave is formed, right? That's why when a supersonic fighter jet goes by, you will hear a boom as it goes. It's the shock wave that's going through, right? So especially in supersonic flows, you throw out a jet of air from the surface and it's going faster than the speed of sound. The air which is coming, it sees that jet as an obstruction. It creates a shock. The minute it creates a shock, there is a pressure jump, and this pressure jump will change the direction of the missile, right? So these are reaction jets. Okay, this is an unconventional control. Small ports in the missile surface, they do what's needed, right? But again, where is this jet coming from? It's coming from the exhaust gases. right? They won't carry little balloons, that's not enough. They'll use the exhaust gases, right? So both these approaches are exceptional in what they can do. They overcome almost all challenges. Missile can do anything it wants. But when you exhaust the fuel supply, these methods don't work anymore, right? So now who's going to carry the extra fuel, right? All right. The people came up with lattice fins. So now the tails are looking different, and they have like these fins inside, like a honeycomb structure. And they move these little fins around to be able to do a whole lot of stuff with the missile, right? Again, they work really well, but they give you higher drag. And you can understand that if you ever put your hand outside the car window, you know that your hand gets pushed back, right? There's a drag on it. So these things are going to drag the missile back. You have to fight that, right? So all of these things are a bit problematic, right? So all of these are taken from the source which I have highlighted below, right? Okay, now we proposed a concept which is almost like a reaction jet, but the difference is we are not using the fuel supply. What we say is, instead of shooting a jet out, I am going to take my missile surface and put a little gap. And if you've gone to the workshop, you know you can do this. Put a little object here and a small micro motor here. Whenever needed, I will just push this out. So instead of the reaction jet creating a blockage on the air, I am going to push out a little thing. I am going to call a protrusion, right? So now this is a mechanical construct. I am not using the fuel supply. I am just using a microcontrolled small little. Think of this finger as a protrusion. This is my missile, it's going, and when I want to, let us say, do this, I say, okay, come up, a shock wave gets created, pressure difference, and missile will roll. Almost works like a reaction jet, right? Alright, so this idea actually came from somebody in the Air Force, right? He was my PhD student, Brijesh Eshpuniyani, he was a wing commander. He did a PhD at IIT Delhi, and I guided him. So he said, sir, can we try this? I said, trying is not a problem, let's see. So we worked on it for 6 years, and it came up with some interesting things, right? So these two things are the computational domain, and I'll go into that later, right? But this is your first indication.
Excuse
that
me, sir.
all of, yes.
Sir, I wanted to ask, you said that the protrusion would come up.
Yes.
Like using a motor or
Yeah.
something like that.
Yeah.
But sir, how would you be controlling the motor? Like you would be having an electrical system for that.
Yes.
So obviously, like you will be needing another source for such a thing.
Yeah, so how would the reaction jet know when it has to come out?
Yes.
So
sir,
there is a
that's-
control system there which is sensing the environment, and it's locked onto a target moves, so that feedback control tells the reaction jet time to go out. The same feedback control is going to tell the motor time to go out, right? I just need a battery there to push it out.
Okay, sir.
That's very straightforward. The same thing which tells the reaction jet tells my protrusion. Same thing.
Okay, sir.
Yeah? Okay, good question. Excellent question. Right? Okay. All right. From here onwards, everything is being done on a computer, right? The physical modeling is done, right? And I'll show you what these grids are, right? So we have a domain, we have a grid on which we solve for everything. Right? We solve for the air speed, we solve for pressure, we solve for temperature. We don't want the missile to get too hot, right? We solve for everything. And then there are boundary conditions that are required in order to match our equations. And I'm going to go through this in detail, right? Okay, so if you are a good programmer, this will take about 6,000 to 7,000 lines of coding, and you can solve such a problem. Okay, all right. These are my these are the scary part, right? So these are my governing equations. Now, how many of you have done differential equations at any level? In 12th, you must have done first order differential equation, right? Those are ordinary differential equations, right? Where each derivative, so suppose I have a function of x, then d dx of fx is derivative of fx. So I can create an equation where I have these derivatives on one side, there are coefficients, and on the right hand side there is either a constant or a function. You are familiar with this much. Now just like there are ordinary derivatives, there is also something called a partial derivative. You are familiar with that too. Wow, you guys are like really doing good. Okay, so what we have is governing equations for fluid dynamics. Right? The thing with fluids is they are squishy things, right? For example, I turn on these fans, the air is going to start flowing all over the place. And how are you going to characterize that airflow? Right? You're going to talk about velocity at any given point. You're going to talk about density. You're going to talk about temperature. So all these are variables. Once you have this squishy thing, the laws of mechanics are the same. The Newton's 3 laws. You apply them, right? You apply the second law, force applied equal to rate of change of momentum. What are the forces in fluids? Pressure is one way to create a force, right? Suppose I take a pipe and I put a high pressure here, low pressure, the fluid will squirt through. Another way is viscosity, right? You are familiar with these terms. Viscosity is nothing but friction inside a fluid. So I can create a frictional effect to move the flow. So all these effects taken together. So you have, if you look at the second line, you see these vertical columns. They carry all the variables. Rho is density, u is velocity, x component, v is velocity, y component, E is energy, right? So you just apply Newton's laws, and with a little bit of paperwork, you can come up with these partial differential equations. There are 4 of them. And then these 4 differential equations I can write compactly if I just create these columns. These are called column vectors. How many of you have done linear algebra? Not yet? You've done? Yeah. You are familiar with column vectors? Okay. Rest of you will be familiar with them soon enough. Okay. So you can set up these equations and write them very compactly. Right? These look complicated because there's a whole lot of variables on the screen, right? Just pen pushing. The laws are Newton's 3 laws. That's all. You need a force to remove inertia, one law. Second law, force is rate of change of momentum. Third law, action equal to reaction. That's all that's being done, but instead of to a solid which is easy to visualize, this is so easy to visualize. The air is not that easy. So you have to use a slightly more elaborate mathematical approach. That's all it is. This can be learnt in maybe how many, 6, 7 lectures, and we can get here. Okay. All right. So we have these really messy looking governing equations, right? Now simple differential equations, right? Suppose I say dy dx equal to sin x. What is y? You will just integrate it. You say, well, y is integral sin x dx, like that, right? Those are called equations which can be solved analytically. These equations for sure cannot be solved analytically. They are messed up, right? So you need a numerical way to solve this equation. Okay, let me give you an idea of what is the numerical approach. When I say df dx, derivative of a function with respect to x, what is this? It is limit delta x tends to 0, delta f by delta x. That's a derivative, right? Now this is talking about a derivative analytically. I can also talk about it numerically. I can take 2 points, take f2 minus f1 divided by x2 minus x1. And I keep bringing these x2 and x1 close enough, they will approximate the derivative better and better, right? So now these can't be solved analytically. So what we do is we set up a grid. Grid is nothing but a whole lot of points which are close together and they are crisscrossing, right? So when you look in the vertical direction, you will see a bunch of y points. Look in the horizontal direction, a bunch of x points. So the x partial derivative can be done numerically, y partial derivative can be done numerically, right? That is where computer science comes in, right? It's all very well to say, but one has to do it and then one has to code it up, right? All right. So in order to solve this, here is your grid. A typical point has a point to the right, points to the left, points to the top, points to the bottom, and each and every derivative can then be set up numerically, right? And how do I set this up? You will set it up in terms of matrices. How many of you know what matrices are? Some of you know, some of you don't yet know. Matrix is essentially an array of numbers, right? And a whole lot, all of this can be set up as massive arrays where each point in the array is a I comma j location. I is in the x direction, j is in the y direction, right? So this goes on. So I can set up each and every term of the equation numerically. Now in compact terms it looks like this. If you ask me how many lines of code will this take to set it up, a few hundred lines. A few hundred lines and you're ready with the gridding part, right? Solving part will take more loops, okay? Alright, then we apply. So this is just numerical method continuing, right? So there is first order differentiation, there is second order differentiation, right? All of that gets done and then we implement it on a grid, right? Along with the grid and the governing equations, you need one more thing, what we call boundary conditions, right? The Newton's 3 laws are the same, but the motion of this little object depends on how much force I put. That force is my boundary condition, right? So hand is on one side of the boundary, this object is in the other side of the boundary, this plane is the boundary, and then something comes and hits this. That's your boundary condition. Same way in an airflow, suppose I am blowing through a straw, right? How fast I blow becomes my boundary condition. And then at every point in the straw, you will get a velocity, right? So just like that, you will see these little arrows near the boundary. So on the left side, velocity coming in, pressure there, density there, so that my code knows what's coming in, these are the conditions. On the top, what are the conditions? On the bottom, on the out. All four sides I have to tell the code, this is the external world, now solve the equations inside. Every time you change the external world, equations will stay the same, code stays the same, but the output will change, right? Okay, alright. So this is all coded up. Then once you get your results, you try and analyze them, right? So I am going to show you some results. I am going to try and explain what these results are, right? So now we know the problem, we are trying to move a missile, right? We know the approach, we've got the equations down, we've got the grid down, we've coded it all up, code works, compilation errors are debugged, then we run it. And output is what? Output is velocity at each grid point, pressure at each grid point, density at each grid point, temperature at each grid point. If I have this much information, I know what is my flow looking like everywhere, right? Then you can plot it, right? So here is my, wait a second, before I come to the plots, I have to cover something even more important. Once you write a code, you need to know that your code is correct, right? There are how many kinds of errors are there, right? There are simple debugging compilation errors, which is to do with syntax and logic. But what if the equations, while coding them, you made a plus sign into a minus sign? The code will still run, you still get an output. How do you know your code is correct? So before you start trusting it, you have to take the code through a validation process, right? So we did that. We took results published earlier by Carter and we said, okay, let us set up what Carter did before we solve our problem. We solved Carter's problem with our code and we compared. So the black dots are Carter's results and the solid line is what our code gave. So we trust it. Yes, we're getting a good fit, right? And on the right hand side, what we did was the grid can be made finer and finer. The more number of grid points I take, the finer is my resolution. That's a trade-off. If you take very few grid points, you're going to get numerical errors. If you take too many, you might have to wait a few weeks before your code finishes running. You don't have a few weeks, right? So you need to make a trade-off. How many grid points do I give? So we do a grid independent study. We keep refining the grid till we see the solution repeating itself. Then we say, well, okay, well, repeating within an error bar. That is our grid. So we did that, we set up all this. Last thing we did is, this is a lab at IIT Kanpur, I was there at that time. So we made this little experimental setup in our lab and we created an experimental scenario. You see a protrusion on the bottom part, right? We created supersonic flow and we measured data, right? Wait a second, okay, just a second. We measured data for both 2D and 3D, right? And we checked the code, whether the code is giving a predictable behavior. It's all right. There's always going to be error. This is one thing about doing this kind of things. You're never going to get zero error. You want an amount of error that you can handle. It's almost like a friendship. You never meet a perfect friend, right? When you have a tolerance level, itna handle ho jayega, usse zyada nahi. Okay, so we are trusting this enough. All right. So we do all this, and this is more of grid independence. I don't want to keep going down this, and you get the basic idea. When we did all these checks, we said, fine, let us look at the results. Now, what have I shown here? These are pressure contours. What's a contour? What's a contour? A closed curve representing what? Something which stays the same. For example, if I tell you, give me the temperature contours in this room, you will say, sir, tell me what temperature are you looking at. I say, okay, 22 degrees centigrades. So you will then measure temperature all over, and all the points which are at 22, you connect them. That's a 22 degrees centigrade contour. It need not always be closed, right? So here you have pressure contours. What we have is on the bottom, we are doing this. This is my wall, and I am going to move this hand up. It's like a protrusion moving up, only a little gently. So that's on the right hand side. You will see the bottom part of the wall starting to rise up, right? And we do that, right? So there are 6 plots here. You will see the bottom wall going up through an angle, right? Okay, now these pressure contours are very interesting. I just talked about the sonic boom. Remember, shock wave gets created. Now, what happens is when an aircraft flies by, you hear one boom, right? Because things are so fast, you don't really hear the formation of that shock wave. That shock wave also is a physically formed entity. The way it forms is through something called compression waves. Compression waves are weaker waves, but when a whole lot of compression waves get together, you've played with those spiral things which move from hand to hand? You do. What are they called? Slinky, yeah, they slink around. Okay, so if you put a slinky on a table and you tap it on one side, what happens? Thing will just go through, and at some point you see a compression, right? So if you observe carefully at the first plot, there are these little waves beginning to rise from the protrusion, and by the second one they are beginning to crystallize into a stronger entity, and right towards the end you will see a nice and proper shock wave. Are you able to see that formation? So this entire thing came out of the code. That's how powerful this is. This is a computer doing everything. We have gone out of the lab completely. One desktop computer with a well written code gives you all the flow physics you want. Okay, and I'll show you that it works. This idea works. Okay, so we did this. So these are pressure contours, right? Then we got the data at many more points. I don't want to bug you with this detail. This is more research level detail, but you can ask me questions later. I want to show you plots which are more interesting to look at. Right, this is the ramp coming down. That was a ramp going up. Now I want to deactivate it. I want to bring it back down. So in the beginning there was a shock wave, and then you see that shock wave starts weakening. Right, this weakening is called expansion waves. The same compression wave, well, not the same, slightly different, but now they are leaving the shock, going away, right? And right at the end, you will see there's just a mass of air that gets blown by. Shock wave is gone. And all this is happening on the missile surface as this ramp moves. Compression waves are being created, getting together to form a shock wave. You hear a boom when it goes by, right? And there's a bigger boom when it lands somewhere. Okay. Hopefully. Alright, so this is stuff happening, and then again this is final level detail, right, which I don't want to bug you with. Now that was a gentle movement of my hand. The original idea was not so gentle. Remember I said plunk, a protrusion will just come out aggressively like a reaction jet. So once we got the gentler thing down, we understood the physics, what was going on. We said, okay, let's now try the harsher thing. Okay, so now there's a protrusion at the bottom which is going to come up. These plots are prettier to look at because they're colored. Okay, so now you see this protrusion coming out. These are also contours, but they are plotted instead of lines, they are plotted as fields, right? So each color on the right hand side, you will see the values corresponding to different colors. Those are pressure values, right? That's called the legend bar, right? Each color corresponds to a certain pressure value, and you can take a look at that plot and you can see how the pressure is changing. So blue is light pressure, green is heavier, and then you will see the buildup of red areas near the protrusion as it comes out. See that? That's your shock wave forming. There's a high pressure jump right across the protrusion. Along with that, in the gentler motion, you don't see this rolling up of the fluid. They are called recirculation regions. Here you do. Right in front and right behind, you will see this fluid going round and round. That's called recirculation. You have to account for these things in the design process, because each of these things affects the pressure. The pressure affects the force, force affects the moment, moment affects how much it's going to turn. Everything is basic mechanics, but done in a slightly more advanced setting. Right? So here we have right at the end this complicated looking flow field. There is recirculation happening on both sides. There are huge pressure jumps happening. There is a red zone which is a shock wave. There is blue stuff behind. Why is there light pressure behind? Because the air is just jumping across, so almost a vacuum region behind the bump. That's very low pressure. All of this is going to affect the forces acting on the missile. Okay, so we did that. Right, and when the pressure, when the contour comes back down, again you will start seeing the shock waves go away, right, and poof, it will clear off the field right in the end. Again, what I want to emphasize here is all of this is done on a computer with about a 6,000 line code. This code was in C. You people are probably going to use more recent languages. This was a C program. Okay. Once you have all this, what do? I've got the pressure. How do I get forces? Right. Now if there's one pressure on so much area, you can just multiply. Suppose the pressure is changing, what will I do? I'll take small areas, integrate. Right. Force will be an integral of the pressure. Perfect. Right. Alright, this is fine. So I had two cases. One was a ramp which moved gently up. The other one is a protrusion at the end of the missile. Right? I didn't put it in the center, I put it at the end. Why is that? Because when I want to roll the missile, I'm going to roll it about its center of mass. Right? Moment is force times distance. So if I create a force right at the end of the missile, I get a larger moment. Right? So that's a more intelligent way of doing things. So we did that, we put the protrusion right at the end. Now I'm going to show you the result which tells you this whole thing is actually alright, which is this. We gave it a challenge. We say you have to execute a 90-degree turn at 3 times the speed of sound. So this is going at Mach 3, 3 times the speed of sound, and it has to execute a 90-degree turn. That means I'm after an aircraft. Pilot is really clever. He's flying like this. He senses there's a missile coming. He says, okay, let me pitch up. My missile needs to be sharp enough to go. Well, I'm not letting you go. It's going to execute a 90-degree turn. We executed it using both ramp type control and protrusion control. Right? In order to execute the ramp type control, the maximum acceleration we felt was 5.6 times g. It took us about 19,000 meters, right? That is 19 kilometers, which is nothing for a supersonic missile. It's going 3 times the speed of sound. 19 kilometers is nothing, right? And it took 25.64 seconds for it to do it, right? And well, that's ramp. Suppose I say I want to go faster. Protrusion is more aggressive. It managed to give a 9.36 times gravity acceleration. Right? This is pitch acceleration. What is pitch acceleration? The acceleration at which this angle changes. I want to stand up. Right? That acceleration. Almost 9.5 times gravity. Okay? And it gave it to me in 11 kilometers. About half the ramp type, and about 15.3 seconds. In 15.3 seconds, here's a missile and it's able to do this. That means this proposed strategy is not so bad. Of course, right now there are a whole lot of simplifying things being done. Everything is being done in 2D. In a real life scenario, you have 3D. That is why when we carried out our wind tunnel tests, I got both 2D data and 3D data. Do you remember that? Wind tunnel, right. So the 3D computational study is not yet completed. We have to complete it. It's more complicated. Then we have to do this kind of a challenge for it, and we'll see whether it works as well as we want it to. 2D is very promising enough to keep pushing forward, right. So we tested the concept and we drew up a whole lot of conclusions, right. Simple model problem with ramp and control elements works. Future work, go 3D. One complication. Second complication, when you talk about airflow, airflow is not always smooth and nice. In fact, it's never smooth and nice. Even if you light an agarbatti, right, about this much distance, the agarbatti smoke rises nicely and then it starts bursting up. That's called turbulence. So when a missile is going through, just like we feel clear air turbulence when we are flying, the missile also feels it. Suddenly it rattles around, right? That effect is not yet included. We have to include it, and we'll see whether it can handle that, right? And then, right now we are just one protuberance. Maybe there we need multiple protrusions. Let's say one on each side, so that I can do pitch up and go horizontally at the same time. All those things are things that have to be done. But the reason I presented this, and I know this is not a typical computer science topic, but it doesn't have to be. You people are computer scientists, you are not limited to doing AI work. You're not limited. If it's work, if it's exciting, do it. But 3 years down the line, you say, you know what, I want to work for DRDO, for the missile system. You can. In a little bit of build up, you can do it. I want to go and work for ISRO for our re-entry, shuttle re-entry. You can. Little bit of work, you can. Right? All of this is doable even for a computer science graduate. It takes about 4 or 5 postgraduate level courses. You'll do a project in a year or two, you're ready to do that. Right? So that was my emphasis here. I don't want to keep talking. I think I've got, that's 13:59, almost there. I'll open it up for questions. Keep the questions not so difficult so that I don't bumble around, but you're free to ask me questions. Was this all right? I mean, was I able to engage people, or were you lost? I know some of you were lost, like looking here and there, like not everybody. Yeah.
So like when you propose the lab concept, so my question is, for the propulsion to come up, like the pin or whatever has to come up, either you'll have to place a hole, or you'll have to make a small part of the missile such that it becomes rotatable at an angle.
Yes.
So sir, my question is that if you kept a hole, won't it affect the airflow during normal movement?
Right, a brilliant question. So during normal movement, this hole is covered from inside. Think of it like this. Suppose this is my missile, both the hands are missile, and then I want to create a protrusion at the center. So what will I do? I'll shift this slightly. So now you're saying there's a hole, but the part which is going to come out, I'm going to place it such that it covers this hole from below. Right? When needed, it goes up. When done, it comes back just to that level. So it's flush. It won't see a hole during normal flight.
Okay, sir.
Got it? Yeah.
Sir, another question is like when it has to come up and the missiles are shot at supersonic speeds.
Yeah.
So at such a speed coming at a perpendicular direction.
Yeah.
That would be very like a very huge amount of force would be required because.
Absolutely.
So how did you overcome that?
No. So suppose you are talking about this thing coming up, it requires a force. What about those large wings that have to move? They require more force. We are actually reducing the amount of force required. You have those large wings. In order to move the missile up, they had to move up. You have to move these large objects. And we are saying maybe you don't need to. Maybe you can move a smaller object and do your task. We are actually being conservative. No problem.
Okay, sir.
Yeah? Okay. But these are good questions. Excellent questions. Yeah. Anybody else?
Excellent, sir. Sir, theoretically we can prove many theories, but what is the practical implementation?
So the way these things work, any missile or any aircraft design, that you go through theory, you go through coding, you go through result and analysis, all the way till you can convince that lab that boss, go ahead and build it up and test it in flight. We think we have a 90% success confidence that you won't waste all that money. Then they will do it. So you are right. At one point, DRDO or some other organization has to take it up, build a missile, and show that it works. But you can't just do that. You have to actually build a whole case up before they will try it out. And then once that works, once you've set out a missile and it locks on and it does its job, then you induct that in your missile force, just like Agnis were created. Then maybe this will be Agni 5 or Agni 6. That's our hope, right?
Thank you, sir.
Yeah. Okay. Yeah.
While the protrusion comes up, whether it's in center or at the back of the missile, if it's back, doesn't it affect the propulsion of the whole missile? Or if it's in center, doesn't it affect the matter that's about to explode?
Right. So there are always going to be control elements in any missile if you want to move it around. Either you have canards or you have wings, or you have tail, or you have reaction jets, or you have fins. So there's always going to be a control element, right? So you have to place it such that your fuel is burning properly.
But during protrusion, there's a sonic boom, as you said.
Yeah, that's there even on the wings. Anything, suppose just an F-16 jet goes by, there's going to be a sonic boom. Anything which flies larger than speed of sound, they're already happening. You're just introducing one more shock wave.
But in the the other sonic booms, they're at the back of the missile or a jet.
No. It's always in the front. Suppose suppose this bottle is my missile. Even without all this, when the missile is going this way, the shock is here. It's always in the front. It's never here. Right? The way a shock wave is formed, the reason it forms, it's a brilliant question for me. When I do this, how do you hear? When I click my thing, this clicking affects the molecules around, and then those molecules affect the next level of molecules, and then this molecule is a wave that comes. It's called an acoustic wave. This acoustic wave comes to you at 340 meters per second, right? So now suppose this thing is going below 340 meters per second, any air here can tell this guy, or rather let me put it the other way, this motion propagates through waves up, and the air knows that something is coming, and then there is a separation. That's why air comes and some part of it goes above, some part of it goes below, right? If it's coming faster than the speed of sound, the speed at which this information is going is slower than the object itself. So before this information can reach there, the object reaches there. Nature adjusts by creating a shock, a sharp change. Otherwise, this physically won't happen. You get my point? So it's always ahead, it's never behind. Shock wave happens to adjust to this very physical phenomena. Brilliant. Okay. All right.
Hello, sir.
Yeah.
My question is, why we sometimes see a pointy head in a missile or any kind of aircraft, or a curved head?
All right. Brilliant question. So it depends on your application. Suppose I am going fast, 3 times the speed of sound, right? Now I want to create as less a resistance as possible, right? So I create a pointy edge, that's called streamlining, right? And in fact, your fighter jets have a spike in the front, right? On the other hand, if I am not so concerned about going that fast, for example, I am coming back into the atmosphere after a planetary mission, my goal there is to slow down, right? Then I make it blunt. I hit the atmosphere, and then this blunt surface creates a bigger shock, and the thing starts slowing down, right? So it's essentially to do with aerodynamics. Yeah.
So you mean to say that streamline body is required for faster movement,
Of course, that is why your Formula cars are more streamlined.
and curved head means
Curve will
economic.
Yes,
friendly?
curve will experience more drag. That's why ambassador cars nobody drives anymore, because there's too much fuel expenditure. It experiences more drag. On the other hand, a sleeker car,
Yes.
like a Toyota, experiences lesser drag, lesser fuel expenditure. Yeah,
Okay, so get it.
brilliant. Ladies not looking good. All 4 questions from guys. No.
Hello. Good afternoon, sir.
Yeah.
Sir, my question is to test all these, do we have any kind of simulation softwares?
Well, okay. So the thing is that there's always a whole lot of softwares available. Some are commercial, some are open source, right? But when you actually work at this level, you usually don't trust anything out there. You create your own code. So this code was done by students at IIT Delhi.
Okay, thank you, sir.
Yeah. Yes. Torpedoes. Yeah. So the way these torpedoes work, the principles are very similar, right? Fluid dynamics. Yeah. Go ahead. Archimedes' principle is to do with buoyancy, right? They don't use buoyancy to fire the torpedo. Buoyancy is used when a submarine wants to come up, right? But when I fire a torpedo, I want to do what a missile does. So I will actually give it a propulsion, and torpedoes are usually given a spin to kind of cut through the water faster. Yeah, brilliant question. Okay, that's 5-1. Not okay. 6-1. Okay.
So my question is that when we use missiles, so for the propulsion, ramjets are used or scramjets are used?
It depends, man. I mean, every option is available. It depends. There are different kinds of missiles. What does the DRDO fleet use? I can't give you an answer offhand.
Okay, sir.
But it's everywhere. Yeah. Between diffusers, compressors. Well, that's a question you'll have to sit in my class and ask me. Then I'll explain it to you. Yeah, we can talk about it later, not here. It requires a lot of time. Look, okay, let me get into it. So it depends on, suppose you use a Venturi type situation, right? At speeds which are at below speed of sound, a compressor will use a reduction of area, a diffuser will use a expansion of area. You have to go into those things. As I said, we can discuss this later, but this is not immediately relevant to this presentation. Yeah, so we'll talk about it. We'll talk about it after this seminar. Yeah. Okay.
Hello, sir.
Yeah.
Hello, sir.
Hi. Yeah.
Actually, I saw your problem. You model this for the 2-dimension, and
Yes.
your future problem is for 3-dimension, I
Yes,
think.
yes.
Actually, I am curious to know about your 3rd-dimension. What is the problem you are facing?
Oh no,
to solve the
there is no
like-
problem. Your governing equations right now are in the XY plane.
Yeah. Okay.
Third direction will include a Z direction. So your equations expand. There will be one more partial differential equation sitting. And the
Okay.
grid, instead of a plane, now there will be a big cube. The
Okay.
number of grid points shoots up.
Okay.
Right? So what you can solve on one computer.
So it's just about the computation.
Yeah, so computational
about the
complexity goes up.
Okay.
Right?
Okay.
Of course, once we get the results,
Yeah.
then it's about seeing whether it's that effective. In 2D, our 90-degree turn was effective. In 3D, everything will change. The pressure will change, density will change, everything will change. With those new values, how effective is it?
Okay.
That remains to be seen. Yeah.
Thank you.
Yeah. Okay. Most recent now, I mean, some years ago they were using titanium grade stuff. Now, right now, I don't know, man. They might have become even better. Yeah, but it's stuff that can handle high temperatures. To answer your question, high temperatures at 3 times the speed of sound, you're going to heat up. The two challenges: keep it as light as possible and as temperature resistant as possible. Yeah.
Sir, ma'am, basically the question is that you told us about the canard and the tail wings, right?
Yes.
So the difference between them was opposite.
Yes.
So like you said, you made two proportions, ramp and the protrusion.
Yeah.
The difference between them is as the same as canard.
Yeah, yeah. Ramp is just a gentler way to do things. Protrusion is a more aggressive way to do things.
So the protrusion would work better for higher angles.
Protrusion would work better if I want to make the missile move faster.
So the drastic change.
Drastic change. But then you have to ask yourself that if I do a very drastic change, is that easier to detect by a radar or a gentler change? A lot of questions come up, right? You don't want another person to detect your missile also. Huh?
So won't it be better to use both of them
Of course,
simultaneously?
if this design works, ultimately your missile is going to have both for different times. Wherever it needs to do a gentler motion, just activate the ramp. Absolutely. Brilliant question. Yeah. Should we wind it up? Or more questions? I'm here. I mean, I'm game. This is my topic, so we can keep going. Yeah. What we have proposed is for supersonic speeds. So, what the ramp idea is to some extent used. I'll have to think about it. It's a good question. I don't have a ready answer for you. Good question. Yeah.
Thank you so much.
Have you set? All right. Thank you so much.
As a closing honor, I would like to request Officiating Director VSET, Professor Dipali Virmani ma'am, and Dean VSIT, Professor Supriya Madan ma'am, to honor our guest with a memento.
This guy is my personal hero. So for me to actually stand here, it's an honor. It's an honor.
Further, I would like to request Professor Nidhi Sharma ma'am to present a vote of thanks.
Good afternoon, everyone. On the behalf of WIPS Technical Campus School of Engineering and Technology and WIPS Technical Campus School of Information Technology, I would like to propose the vote of thanks for the eminent resource person for today, Professor Brijesh Eshpuniyani, who explained the intricate topic of missile system in such an interesting and simplified manner. The topic was indeed multidisciplinary in nature and as well as multidimensional in nature. So with inputs from mechanics, physics, mathematics, and programming also. And lastly, aerodynamic engineering. Thank you, sir, for such an enriching presentation. Further, I would like to thank Honorable Chairman, sir, Vice Chairman, sir, for always being so supportive, for organizing such events. I would like to thank Supriya Madan ma'am, Dean VSIT, and Officiating Director of VCNT, Professor Dipali Virbani. I would like to thank all the colleagues, faculty colleagues of VCET and VCNT. Thank you so much. And lastly, I would like to thank all the students of VCET and VCIT for being such a nice audience. Thank you. Also, I would like to thank our PRO, Prachi, for arranging the event.